Hello, this will be the, I don't know, fifth video probably that you're watching, if you're watching all of them. And in this one, I'm going to show you how to set up an indoor analysis for butterfly. I assume you have already watched the outdoor one because I'm not going to cover some of the details that I covered there. Not that I covered all the details, but this probably will be shorter because most of the workflow is very similar. And the only difference is how you prepare the geometry. To do so, I just go ahead and open uh, the same folder, and interestingly enough, like I think I fixed this. There should be a folder called example files. Inside example files, go ahead and open 020 indoor airflow. There are 2D cases for both of them, but we just go with 3D right now. Okay, let's see what is this case. So this case is a room that has one window on one side and then 3 windows on the other side. We know this one is an inlet. We know this guy wants to be outlets, will be outlets for us, and then the rest will be walls in CFD world. So the only difference here is instead of setting it up like the outdoor workflow that you had, some geometry you put it to create a wind tunnel for you, is you have to prepare the geometries one by one for every group of geometries which have the same boundary condition. So in this case, for inlet, which is this surface here, the boundary condition is an inlet, right? So the way I'm doing it here is we use this component that you can set up an inlet with the velocity vector, which basically says where the wind is coming from and like what is the direction and speed. You can, it's a common practice that, okay, this is a little bit slow, that some people use volume flow rate. So you can set it up with volumetric flow rate, especially if you're setting up like an HVAC system or something like that. And there is an example for HVAC in the example files that you can check if you're interested to use that. Then I name this west window, which is my inlet, and I set the refinement to 2 and 2. The global refinement level is 0, 0, so I just set it 2 and 2 for this inlet. For the outlets, they're down here. They're called east window. The geometries are all here, and again, all the geometries are in the same component, so they will be grouped together because they have the same boundary condition. And then I set up the boundary condition. Again, I leave the temperature empty because I'm not interested in this example to model the heat transfer. So I will be using only the boundary conditions with no change in temperature. And then, so that was inlet, this is outlet, and the rest are the walls. For you, if you're asking yourself now, how do I need model this? So this is not like how Honeybee is, for example. You have to subtract the geometries. So you can see the surfaces that they have, the wall doesn't have the window anymore. This is just one thing to keep in mind about preparing the geometry. So with that, I get a delay when I do zoom in and zoom out, probably because at the same time I'm doing other stuff on this computer. With that, you have all your geometries, and this time, this is very similar, again, if you're a Honeybee user, to the case that you create a Honeybee case surface by surface, or you do mass to zones. So you create a wind tunnel, or in cases like this, you are creating a case from surfaces, or geometries in this case. So you connect all these butterfly geometries here to this component, and you name it. Here is indoor airflow, you add a name, and then you set up meshing parameters. In this one, and actually we have time, so let's talk about this meshing parameters. This is a component that has 4 inputs, and these 4 inputs are chosen from all the other meshing parameters that you have in OpenFOAM, because these are the ones that we felt you need to set up without running the analysis. These are the most critical ones that you want to set up. And the concept was you can set them up and then don't run anything here and run it on cloud or something. So that's why you have access to this before, like when you want to create the case, before doing any meshing stuff. But you can overwrite them. So the first two, the cell size and the grading, are the ones that will affect the block mesh stick. The location in mesh and global refinement level are the ones that are affecting the snappy hex mesh. So for these two, if you go here and see the block mesh, you can actually override them here. And for snappy hex mesh, this is the location mesh here. And then if you want to change the global reference, you can change it here from inside the snappy hex mesh deck. Okay, with that, let me go ahead and write this case. One thing that is worth mentioning here is if you run the analysis once and then you want to purge the case, this component is here to let you remove the block mesh, snappy hex mesh result, or post-processing result if you have any of that. By default, it's set to false, assuming this is your first time running the analysis. So it generated the block mesh. As you can see, these are the points that shows you the size of the block mesh in block mesh dict. Butterfly by default makes one extra cell instead of snapping it to what you have as the geometry. The reason for that is to make sure that the snappy hex mesh will touch all the boundary conditions that you have on the edge. Sometimes because of the tolerance that doesn't happen correctly. And then also to help to have a better edge conditions, especially if you snap to the geometries. This is more helpful to have a larger box and then remove the extra stuff from outside. If you are not interested in this, you can set the expand block mesh to false. And I do it here so you can see what happens. So now you can see the bounding box. Basically, the points are as large as your box. Again, by default, it is the true. And unless you have a good reason, I suggest you to leave it as it is, like this. So now let's go ahead and run the meshing process one by one. So this is the block mesh. And again, I'm doing multiple stuff right now, so everything is slower than what it should be. Let's go visualize this. Turn the preview on. So this is your block mesh. Again, as you see, you can see like you have one extra cell on each side of the box from your geometry, which is okay. Which and if you don't know enough about like how OpenFOAM works, so in a snappy hex mesh based on the location in mesh, which is by default the center of all your geometries, which will be inside the room, the extra meshes from the sides will be removed. So let me go ahead and run this snappy hex mesh. Oh, the solver was on, so it started running the analysis. I just closed this. I didn't want to go there. Oops. Okay. Okay, so the reason was like these two was on. I turned them off. Let's imagine that this didn't happen. Before going there, I want to load the snappy hex mesh so you see what happened to the mesh. So that was the block mesh. You can see now what happened. So the mesh is removed. You can see because the refinement for these surfaces was set to 2. Now they're meshed an extra time. And there is a lot more that we can talk about when it comes to snappy hex mesh, but to learn more about meshing stuff and how a snappy hex mesh works, go and check this document, A Comprehensive Tour of a Snappy Hex Mesh. that covers all the stuff for each step. Most of the stuff you read here is already automated in Butterfly, but to have the knowledge and to know what's happening in the background is really critical, especially for CFD analysis, to make sure you are getting what you really are trying to get out of the analysis. One thing that is good to show now is one of the features in OpenFOAM is that you can check mesh. And we have a component for that, which I assume is this one. It's not part of the workflow of setting up and running the analysis, but it's always good to check your mesh after the meshing and see if there is any error. So I go here and run it. And if we run the check mesh, it will give you the maximum non-orthogonality and the average value that you have. Again, this is like a very like the edges and everything. This is not a really complex case, and everything should be fine. But then these are values that you can use to modify the recipe. Again, I'm keeping myself not to go there. Just disregard all the stuff that is up there, and there should be a way to remove them from the log because that's not what we really care. But you can see here, it did the checking geometry. It gives you a report about mesh, and it says the mesh is okay. If it wasn't okay, you would give it will give you an error. Again, check the document and see what is the relationship between mesh non-orthogonality, for example, and then setting up the FV schemes, for example, in your case. Or here you can see we have a component that based on the maximum non-orthogonality, it gives you a suggestion for the FV scheme, which is again is prepared based on one of the documents which is available out there. But let's not go through those details. Okay, meshing is done. Let's go here. We're good to go and run the analysis. Just one thing which is different in this example, we wanted to showcase the ability that you have to change any of the parameters that you have in your case or customize any of the parameters that you already set in your case. By that, I mean, for example, in this case, we already set the U value, the U input for the wind speed for my inlet. We set it to 1.2, right? We come all the way here, we run the mesh, we run the snappy hex mesh, and then we see, oh, like this should change to 2.5. Was it 2.5 there too? No, 1.2, okay. This should change to 2.5. One way is to go back here and change it. And actually you can change it and then disconnect the case from here and connect it back here because you already have the mesh already set and there is no change that you really need to rerun the mesh. You can just pass these two steps. But the other way is to come here and create what we call a solution parameter and add it to the case. The good thing about this is the flexibility that it gives you. So you can come and literally change any field inside any dictionary as far as you know what do you want to change. So now we want to change the value for the inlet, which is under boundary field for the west window, which is the name of the inlet. And what is the file name I'm looking at is U. What are the values? Is this values? You just add it here, and then you can add it to additional parameter. You can use the same methodology to overwrite the whole file. If you have, for example, something that you think it's not set correctly or you don't like the setting that we have, you want to customize that, you can use solution parameters to do that. If you read the documentation, there are ways even to make it time sensitive. So it will change like at time step like 200 or something. And then you can say if you want this thing to replace the values already in the file or you want to update them. What does it mean? So if I turn off the replace, then the whole boundary field will be replaced with the west window value and everything else will be removed, which is not what we want. We just want to update the west window thing. So I can actually show it to you in the folder. So I think for the users who are more advanced in use and have used OpenFOAM before, this should make sense easily. But if you haven't, this might be a little of what is he talking about exactly. So indoor airflow is here. Inside the 0 folder, for example, you see these files that are the files that I just changed one of them. And keep in mind, if you're changing anything in the time folder, you don't want to change it while the analysis is running, because that means you are basically creating a new analysis from the start. You know, like you can create the solution parameter for any of the dictionaries. It can be in 0 in time folder, it can be in systems, any of these files, but then for the 0 one, you just want to write that before starting the analysis. Let me go inside U and show you where this thing is. So inside the U dictionary, there is a boundary field, and this is the one that I really want to change. Keep in mind, this is not something that you can undo. So if you change it, it's not like if I disconnect this will go to value 1 point whatever. So this is something that you write and it will be there. Maybe we will add an undo there, but it might be like just an overdo. We don't really need that. So if I go back and set this to 1.5 and write the case, first of all, you will see here that it says the boundary is changed from 2.5 to 1.5. Let's go and check inside the file. It says, oh, there is a change. And now you can see this value is changed to 1.5. Basically, whatever change you make here, it will change the text file here. It will save you a lot of time for not dealing with the files there. But what is important here, again, is the great thing about all this stuff, having all this stuff in Grasshopper, is you can automate everything. And then if you have a logic, it can happen like for all the stuff that you have. You don't want to open the text file and edit it and come back here. That's why you have this here. With all that, everything else is very similar to the outdoor analysis. I can just run this, and this should be done in 600 runs. Like, where is the control dict? We have like maximum end time of 5,000, which we will never reach there because it will be converted in 606. So let me run this, and then let's watch the result while it's running. Oh, and let me turn off the preview wherever I turned it on. And you see, in this case, I set the interval to a smaller number, so it's harder to interact while the analysis is running. Okay, this is the place. A preview of the run. So you can see it. In this case, I have more points. I'm checking both the section and here horizontal surface. Again, this is a 3D run, so you can just put it everywhere that you want and check the results. And again, you can change all the visualization stuff, because this is technically the ladybug stuff that we're using here. And you can change check the values for residuals. You can plot them, and all those stuff that you already should know from ladybug. And here we go. So that's the pressure, and these are the wind velocity, and the color of the vectors are also the velocity. And now we can see the range of velocity, which is between 0.14 to 1.5. And my wind speed was 1.5, so that makes sense. We are in an acceptable range. Okay, I hope you enjoyed this video and it kind of helped you to understand how Butterfly works. And again, there are more example files that you can check yourself. You can read the documents from OpenFOAM and educate yourself about that. I will try to do more videos over the time, or again, as I said, I hope somebody else takes over that and do better videos. But these are the videos that I hope to get you started for the first release. Thank you for watching. Post your questions on the Grasshopper forum, not under this video, and let us know what you think.